Hello and welcome back to Calculus. First, I'd like to thank all the nice people that support this channel by liking and subscribing. In the last video, we spoke about the intuition behind volumes of revolution, and the end result we got was a formula for calculating those volumes, which is pi times the integral from a to b of the function squared and dx. So today we will apply this formula and we'll take a look at three examples which describe the three different cases of volumes of revolution. So for the first example, we have a function e to the power of 1 minus x, and we're asked to find the volume on the interval from 0 to 1 when this function is rotated 2 pi radians about the x-axis. Please recall, 2 pi radians is simply 360 degrees, so that means we make a full rotation around the x-axis. First, let's sketch this curve on a graph to help us visualize. Here on the graph, the orange lines denote the interval 0 to 1. So that means only this part of the function from 0 to 1 is going to be rotated around the x-axis to form a volume. Now, in order to find the volume of this shape, we can use our formula pi times the integral. In our case would be from 0 to 1. Next, we take our function e to the power of 1 minus x, and we have to square it. Since we have a power and a power, it means that they can be multiplied, forming e to the power of 2 minus 2x. Next, we have to find the antiderivative of our red function. Good thing is, it is an exponential function, and technically nothing changes. It still stays e to the power of 2 minus 2x. However, we have a composite function, meaning that in the exponent there's another function. So we know that we have to divide our antiderivative by the derivative of the exponent, in this case, negative 2. All of this then is evaluated from 0 to 1. Once you plug in 1 and 0 and subtract them, the answer that you should get is pi over 2 times e squared minus 1. If you do not have a calculator, this would be the answer you leave. If you do, you can technically say that it is approximately 10. Now the unit here would simply be cubic units. You can also write this as units raised to the power of 3. Quite simple and not too hard. So let's move on to the next example. For the next example, we have a function x squared plus 1 over 2. It is bounded by the lines y equals to 0.5 and y equals to 3. And now this function bounded by these two values is rotated around the y-axis by 2 pi radians or 360 degrees. So let's first visualize this on a graph. Please note that y equals to a certain value corresponds to a horizontal line on the graph. And now please note one more thing. Our graph between these two y values is now rotated around the y-axis and not the x-axis. You can kind of imagine that if you rotated and formed a solid shape, you would get something like a bowl or a cup. Well, what exactly do we do here? Please recall that for the examples of area between curves, we also had a similar situation where area was evaluated with a function of x and not y, because the x and y axes were interchanged. So here, a similar thing would happen. Our function y equals to x squared plus 1 divided by 2, we have to first express it as x equals to something in terms of y. So step number 1, we can first multiply both sides by 2 to get 2y equals to x squared plus 1. Next, we can move the plus 1 to the other side, and you would get 2 minus 2y minus 1 equals to x squared. And finally, we can take the square root of both sides to get the square root of 2y minus 1 equals to x. So now we have a function in terms of y instead of x. Now we can use that same formula for volumes with integrals. The volume here would be equal to pi times the integral from the lower y value 0.5 to the upper y value of 3. And we take the integral of our function 2y minus 1 squared, and in the end, instead of dx, we will write dy. So the idea is the same, only the variable changed. Now, since we have a square root and raised to the power of 2, they cancel each other out, and the only integral we have left is the integral from 0.5 to 3 of 2y minus 1 times pi in front. Then we get our antiderivative function, and we have to evaluate this. And I can tell you the final answer is going to be 6.25 times pi in cubic units. So essentially, the idea is the same, only here we had to take one extra step in order to express our function in terms of y and not x. Okay, now let's move on to the very last example where we have volume between two different curves. For the final example, we have two functions. One of them is f, the square root of x squared minus 2, and the other is g of x, x squared over 4. And we're asked to find two different volumes. The volume when they're both rotated around the x-axis, and the volume of when they're both rotated around the y-axis. So once again, let's first visualize these two functions on a graph. As you can see, this time in our exercise, we are not given bounds because these two functions intersect at two distinct points, this one right here and this one right here. So in order to establish the bounds of our integral, we have to first equate these two functions to each other and solve them. Once I equate them, I square both sides to remove the square root, and then I can do cross multiplication, which would give me 16x is equal to 2x to the power of 4, or in other words, 8 is equal to x to the power of 3. And I think two very obvious answers are x equals to 0 or x equals to 2. So that means these would be the bounds of our integral from 0 to 2. Now that we have the bounds, we also know which function is on top, in this case the blue function f of x. We can find the volume rotated about the x-axis. Here, to find the volume, the formula actually doesn't change that much. Essentially what we have to do is take the square of one function and subtract the square of the other. Now, the first function would be the upper one, in our case the blue function f of x, and the one that is being subtracted is the lower function g of x. If we put our functions inside, what we get here in the front is x over 2 minus x to the power of 4 over 16 dx. Next, we find the antiderivative function x squared over 4 minus x to the power of 5 over 80 evaluated from 0 to 2. You should be able to do this very fluently after so many parts of integration and calculus in general. The answer we get in the end is pi times 1 minus 3 over 5, or even more simplified, it's 3 pi over 5. Now this wasn't very hard, but what about the volume when we rotate both of our functions about the y-axis? Once again, we have to take an additional step which changes our function in terms of y instead of x. So for the blue function, we had y equals to square root of x, meaning now this is going to be y squared equals to x over 2, and then 2y squared is going to be equal to x. For the other function, we had y is equal to x squared over 4. So that means 4y is equal to x squared, and then square root of y times 2 in front is going to be equal to x. However, now we have another problem, because the bounds of the integral are not going to be the same, since now we have new functions in terms of y. Meaning, in order to find the bounds of the integral, I have to first calculate 2y squared equated to 2 square root of y. Now, I think it is pretty obvious that the answers here are 0 and 1. However, also, we have another problem because now we don't know which function is on top and which function is on bottom. However, I can show you here that by flipping this function a little bit and then also mirroring it, we have successfully interchanged the x and y axis, and you can clearly see that the green function, technically g, is now on top. So what we get is the integral from 0 to 1 of the green function 2 square root of y squared minus the blue function 2y squared squared, and everything is times pi in front. And pardon me, here in the end, it's not the x anymore, but the y. Now I challenge you to solve this integral on your own, and the answer that you should get at the end is 6 pi over 5. And that is all about volumes of revolution. In the next video, I will show you kinematics. Now please recall back in part 13, when we were speaking about applications of derivatives, we have already done kinematics once. However, integrals also have their own set of applications that are related to kinematics, and I will definitely show you them in the next video. So, I hope to see you there and have a nice day. Bye!